Hello and welcome to this lecture. We saw the bivariate case, the simple case where it was a simple combination of u and v, and now we are going to see the bivariate Gaussian case where it is more general. Okay, so notice what we are going to do here. We are going to have once again uv being IID normal 0 1. Okay, so these are independent, and z1 z2 is going to be a linear combination, but both z1 and z2 are going to be linear combinations. If you remember before, z1 we let it to be u, z2 we let it to be v, right? We didn't do the general case. Now we are going to do a more general case. Notice what I am doing here, z1 z2, I have put an arbitrary 2 by 2 matrix here, a b c d u v, and then I am also adding a constant mu1 mu2. Okay, so what happens after you simplify this formula is z1 becomes au plus bv plus mu1, okay, and z2 becomes cu plus dv plus mu2. Okay, so these are z1 z2. Now if you notice, z1 is a linear combination of two Gaussians, independent Gaussians. z2 is a linear combination of two independent Gaussians. Anything like this becomes jointly Gaussian. Okay, so if you have independent Gaussians and if you do a linear combination of them, add some constants to them, you get jointly Gaussian random variables, meaning z1 and z2 individually are normal, but they are also jointly normal. They will have a joint distribution which is normal. Okay, how do you study these guys? Okay, so remember the important lesson is for jointly Gaussian random variables, means, variances, covariances are enough. If you study them, the entire distribution is a function of these quantities, means, variances, covariances. That's a powerful property of jointly Gaussian distributions. Okay, so we have to only worry about mean, variance and covariance. Okay, there are only two random variables here, z1, z2. First we will do mean. If you do expected value of z1, expectation is linear, so it goes in. Expected value of u is 0, expected value of v is 0. Expected value of mu1 on the other hand is a constant, so it will just become mu1. So you see z1 has mean mu1, z2 has mean mu2. Okay, expected value of z2 has mean mu2. I mean it becomes mu2, so z2 has mean mu2. Okay, so means are very easy. Variance also is very easy. Variance of z1, supposing you want to call it sigma 1 squared, it's going to become a square plus b square. We have seen this before, right? Variance of z1, you can ignore mu1, it's just a constant addition, and a square plus b square becomes the variance. It's quite an easy calculation. If you don't believe me, do that. You can do expected value of z1 squared minus expected value of z1 whole squared, you will get the same quantity. Okay, it's a good exercise to try and do. Similarly, variance of z2 is, I'll denote it sigma 2 squared, it's c square plus d square. Okay, so notice it's very easy to do, right? So when you do arbitrary mix with uv and you get 2 z1 z2, the means and variances are quite trivial to calculate because these are direct linear combinations, affine combinations maybe with mu1 mu2 of u and v. Okay, so it's easy enough to do. What about covariance? Covariance we know is expected value of z1 minus mu1 times z2 minus mu2. Okay, so if you do that, you're going to guess multiply au plus bv with cu plus dv. So ac will survive, bd will survive, ad and bc will go off to 0, right? So you can see when you multiply these two guys, z1 minus mu1 into z2 minus mu2, it's au plus bv times cu plus dv, right? So when you multiply these two, you will get ac u squared. So when you take expected value of u squared is 1, so you will get ac. Likewise, when you multiply these two, you will get bd v squared, and then expected value of v squared is 1, so you will get bd. But when you do ad and bc, that will go off to 0 because you get a uv and expected value of uv is 0. Okay, so you notice here the correlation is AC plus, covariance is AC plus BD, and the correlation coefficient is AC plus BD divided by sigma 1 sigma 2. Okay, so sigma 1 sigma 2 is root of a square plus b square root of c square plus d square, but nevertheless you get a correlation coefficient. So the joint distribution of z1 z2 is a function of mu1 mu2 sigma 1 square sigma 2 square and rho. Okay, so that's one way you can easily see. But I've often seen, I mean, you can write down the joint distribution as one big ugly formula with z1 being replaced with something and all that. I'm not going to write that. I will let you look it up if you're interested. But to me, for bivariate Gaussian, here is a very interesting little analogy. Okay, so notice what has happened here. Z1 Z2 became normal mean mu1 plus comma sigma square, mu2 comma sigma 2 square, and rho Z1 Z2 became rho. Okay, I'm going to generate Z1 Z2 in another way, as a linear combination of uv, but not like this, but some other way. Okay, so notice what happens here. Here is the interesting little idea. I'm going to go to a z1 tilde, which is the normalized version of z1. What is normalized version of z1? z1 minus mu1 by sigma 1, right? what is this? This I'm going to call u. Okay, this is, if you notice, normal 0 1, right? Z1 minus mu1 by sigma 1 is normal 0 1. So this I will call u. Okay, don't worry about this u. This is the u that I'm calling here. Okay, this is Z1 tilde. What happens to Z2 tilde now? Z2 tilde is Z2 minus mu2 by sigma 2. Okay, and that, it turns out, I can always write as rho u plus root of 1 minus rho squared v, because Z2 tilde is also normal 0 1, and interestingly the correlation coefficient between these two is rho. Okay, so instead of worrying about the distribution of Z1 and Z2 and dealing with complicated formulae, I will only worry about the joint distribution of Z1 tilde and Z2 tilde and do all calculations there. If I have to do probability calculations with Z1, Z2, I can always translate it into probability calculations involving Z1 tilde, Z2 tilde, and for that I know the joint PDF because it has the simple form, right. So this is the way in which I can go from reduce the general case to the simple case. Okay. So the general case is not so interesting in the bivariate case. You can always reduce it to this very simple case and do calculations with it. Okay. So hopefully this gives you an idea of how the general case works for bivariate Gaussians. Arbitrary linear combinations of uv with some constants added, you get Gaussians, you compute the correlation coefficient and then normalize it like this and think of it as the simple case, and you can go ahead and do some problems with that. Okay. Important properties for bivariate Gaussian. Let's say x and y are normal 0 1 and the correlation coefficient is rho. Uncorrelated implies independence. So now this is a powerful property for Gaussians. It's not true in general. Okay, independence implies uncorrelated, but uncorrelated generally does not imply independence for random variables. So when rho is 0, x and y are uncorrelated. When x and y are jointly Gaussian, x and y are independent when rho is 0. So that becomes a powerful property for jointly Gaussian random variables. The other important property is if you do a linear combination of jointly Gaussians, remember x and y are normal 0 1 and their correlation coefficient is rho. If I do a linear combination of x and y, it also ends up being Gaussian. Okay, any jointly Gaussian random variable, if you do linear combination, you get jointly Gaussian. Why is that? It's easy to see. Ax plus by is ultimately a linear combination of some independent Gaussians. Okay, so Ax plus by becomes Gaussian. In fact, this is a defining property for jointly Gaussian random variables. We defined it differently, but usually this is considered a defining property for the jointly Gaussian random variables. So how do you find mean? See, once I know it's Gaussian, to characterize the distribution of W, I only need its mean and variance. What is the mean? Mean is 0. You take expected value, which is a times expected value of x plus b times expected value of y. These two are 0, so mean goes to 0. What about variance? Now we have to be slightly careful. Okay, mean is 0, so variance is just expected value of w squared. When you do w squared, you're going to get a square x squared plus b squared y squared plus 2ab xy. Okay, now expected value of x square is 1, expected value of y square is 1, but expected value of xy is not 0, right, because x and y are correlated. So you will get a 2ab rho. Okay, so you will get a squared plus b squared plus 2ab rho, and this becomes your variance. Okay, so notice how the variance has a rho factor in it because the x and y are correlated. Okay, so this is how you deal with linear combination of independent Gaussians. If you have a pair of linear combinations, W1 and W2, ax plus by, cx plus dy, this again becomes bivariate Gaussian. So it's very easy. You can do mean will be 0. You can do variance, a square plus b square plus 2ab rho, c square plus d square plus 2cd rho. Then you also need rho covariance for W1, W2, right? Because mean is 0, it's just expected value of W1, W2. So I'm going to multiply these two. So I'll get AC x square plus BD y square plus AD plus BC xy. So notice this becomes AC plus BD because expected value of x square is 1, expected value of y square is 1. But then this doesn't go to 0. You get AD plus BC times rho. That rho enters the picture there. So the covariance, the correlation coefficient between W1, W2 is AC plus BD plus AD plus BC rho divided by sigma W1, sigma W2, and sigma W1, sigma W2, you'll have to plug in this formula. So it's a complicated looking formula, but eventually W1 and W2 are bivariate Gaussian. I know their means, I know their variances, I know their correlation coefficient, which means I know their distribution. Okay, so this is how you deal with linear combinations of jointly Gaussian random variables. Okay, so here are a bunch of problems which we can now hope to solve given our knowledge of what these things are. Okay, so suppose x, y are normal 0, 1 and they have a correlation coefficient rho. Okay, so normal 0, 1, expected value of x, y becomes correlation coefficient, right? It becomes rho. So, you have to compute the following probabilities using the Q function. What is the probability that x is greater than y? Okay. Now, when rho is 0, probability that x greater than y is half. Okay. So, it is very easy to write down. But when rho is non-zero, we have to see what happens, right. So, maybe it become half. So, I do not know, we will have to see what happens to that. So, let us write this down and try and work out some of these problems. Okay. So, x and y are normal 0, 1, they are not independent, rho is expected value of xy, okay, and you are asked for probability that x is greater than y. So, for all these problems, it is good to define w as x minus y, and then this simply becomes probability that w is greater than 0. Now, w is normal, okay, mean is 0 and variance is whatever, right. So, I mean variance is 1 plus 1 minus 2 rho, isn't it? So, that is the variance, but it does not matter, normal 0, mean 0 implies this is just half, okay. So, x and y, whatever the correlation is, probability x greater than y is a half, okay. So, what about x greater than y plus 1? So, this will be a little bit more different, probability that x is greater than y plus 1. So, here you will have to define w to be x minus y minus 1. So, that this becomes probability that w is greater than 0. So, this is normal with mean minus 1, and for variance this minus 1 does not matter, only x minus y matters. So, it will just be the same as there 2 minus 2 rho, okay. Now, what is probability that w is greater than 0? Mean is minus 1. So, it is going to be, if you want to write it in terms of q functions, it is going to be q of 0 minus minus 1 by square root of 2 minus 2, right. So, it becomes just q of 1 by root 2 1 minus rho, okay. So, that is a very easy calculation. You can see why these are very easy. Once you find w as linear combination, you know it is Gaussian, you just have to evaluate its mean and variance. Once you find its mean and variance, you are done. Okay, remember x and y are correlated, that is why the variance does not simply become 2, 1 plus 1, 2, it is 1 plus 1 minus the 2 times xy expected value. So, you get the 2 rho on that side, okay. So, the correlation plays a role here, okay. So, 2x plus 3y greater than 4 as a similar formula, you will have to do it, I am not going to repeat that here. Okay, so, let us look at the second question. UV are IID normal 0, 1, find a condition on ABCD such that AU plus BV and CU plus DV are independent, okay. So, remember AU plus BV and CU plus DV are going to be bivariate Gaussian, right. So, they are jointly Gaussian, which means uncorrelated is the same as independent, okay. So, how do we do this? So, let us look at that. So, expected value of AU plus BV times CU plus DV, okay. U and V are IID normal 0, 1, okay. So, this is going to be AC plus BD, right. So, if for these two, let us call this W1, W2. So, for W1 and W2 to be independent, we need AC plus BD to be equal to 0, okay. So, now this is so easy to do in so many different ways, right. So, you can of course do some very simple choices, but you can also do so many other interesting choices. So, for instance, you could pick A equals C equals 1 and then B equals 1 and D equals minus 1. If you do this, it goes to 0, right. So, what it means is U plus V and U minus V are independent, okay. So, these are things that people find a little surprising. See, U and V are contributing to both U plus V and U minus V, but then they are statistically independent, because the way that works, it is ending up like this. So, this is an interesting case. Of course, I mean, if you do so many other simple things you can do, but this is a very interesting case where you have independence, okay. So, yeah, that is a non-trivial example I gave you of that. Okay, so let us look at the next problem. UV is IID normal 0, 1, x is u and y is u by 2 plus root 3v by 2. So, you can see x and y are now correlated, and the question being asked is what is probability of x greater than 0, y greater than 0. So, let us write this down. X is u and y is, so you can see rho is half, right. So, rho has been picked as half, and then root 3 by 2 is root of 1 minus rho squared v, and then the question asks probability that x is greater than 0, y is greater than 0. So, you can translate, see, remember u, v are IID normal 0, 1. Okay. So, this question in the xy plane, it asks you to find, in the xy plane, it asks you to find this area. Okay. I have to translate this into the uv plane. In the uv plane, I can easily find any areas because uv is circularly symmetric. It's normal 0, 1. I can, my theta is uniform, my r has a Rayleigh distribution. So, I can calculate areas very easily. But how do I translate this into uv? So, you have to say that. So, x greater than 0, y greater than 0 is the region in the xy plane. Okay. Now, x is the same as u, so it goes to u greater than 0. So, u greater than 0 is on this side, right side, and then y is half u plus root 3 by 2 v greater than 0. Okay. So, this basically means v is greater than minus 1 by root 3 u. Okay. Is that all right? So, u greater than 0 is all this side, right hand side, this part is u greater than 0, and now for this you have to draw the line v equals minus 1 by root 3 u. So, where is v is minus 1 by root 3 u. So, you will have this minus 1 by root 3 is an angle, right. At what angle will you have this? It should be like, it will be a line like this. This is let us say v equals minus 1 by root 3 u, and what will be this angle? This angle will be tan theta has to be 1 by root 3, and that will be pi by 6, isn't it? So, I think that is correct. Okay. So, this is pi by 6. So, this is tan theta as minus 1 by root 3, and you get the angle as the slope. Okay. So, that is that. So, now if you want to look at the area, this area here, y x greater than 0, y greater than 0 is u greater than 0. So, it's all everything on the right hand side, but then v greater than minus 1 by root 3 u, which means everything on the right hand side of this line. Okay. So, the actual area here is this area, isn't it? This area. Now, this area is like a angle, no? This is 90 degrees, pi by 2, and this is pi by 6. So, the total angle here is pi by 2 plus pi by 6, which is, you can do the calculation here. This is 3 pi by 6, so 4 pi by 6 or 2 pi by 3. Okay. So, that is the overall angle here. So, 2 pi by 3 is the overall angle here, and remember it is circularly symmetric in uv. So, the probability of u greater than 0 and v greater than minus 1 by root 3 u is the probability that theta lies between minus pi by 6 less than theta less than pi by 2, and that is just interval of pi by 3. So, 2 pi by 3 by 2 pi, and that is 1 by 3. Okay. So, it is slightly more difficult calculation. You have to adjust this, move from the xy domain to the uv domain, and in uv domain it is circularly symmetric. So, convert this entire region into simply an angle theta lying between minus pi by 6 and pi by 2, and that is 2 pi by 3 by 2 pi. Okay. So, the last problem was slightly more complicated, but hopefully the first two were interesting enough. Okay. So, that concludes the bivariate Gaussian, the general case, and you see that the general the distribution is going to have that elliptical type PDF, and the scatter plot. From the scatter plot you can infer the row very easily. These things are very important ideas in bivariate Gaussian. Very importantly, the means, variances and the row, the covariance correlation coefficient, is all that matters for the joint PDF. So, in any situation, try to calculate those things and reduce your calculations to everything reduces to simple calculations at the end. Okay. Thank you very much.